this video, we're going to talk about improper integrals. So the definition of the definite integral, the integral from a to b of f of x dx, requires that the closed interval from a to b be a finite interval, and the fundamental theorem of calculus requires f of x be continuous on that interval. So this section is going to discuss intervals that don't satisfy these properties. Either a or b is not a finite number, one or the other could be negative infinity or positive infinity, or where there's a discontinuity. So if you say a or b is replaced with infinity, or if there's a finite number of infinite discontinuities, then the integral here is said to be an improper integral. A function f is said to have an infinite discontinuity at c when from the left or right the limit as x approaches c of f of x equals infinity, or the limit as x approaches c of f of x equals negative infinity. So to think about how we're going to evaluate an improper integral, let's consider the following. We've got f of x equals 1 over x squared, and we want to talk about how to evaluate the integral from 1 to b of 1 over x squared dx. So basically what's going on here is we're starting at 1, and we're picking a value of b, and we're saying, okay, let's find the area under that curve from 1 to b. Now if you want to find the area under the curve as from 1 to infinity, you can think about what happens to this integral as b approaches infinity, and that of course would be a limit. So let's do this. I've got the integral from 1 to b of 1 over x squared dx, so I'm going to write that as the integral from 1 to b of x to the negative 2 dx, which will be x to the negative 1 over negative 1 from x equals 1 to x equals b, or negative 1 over x from 1 to b. So that'll be negative 1 over b, plugging in the top bound, minus negative 1 over 1, plugging in the bottom bound. This becomes a positive 1, so we'll have 1 minus 1 over b. And now we take the limit as b approaches infinity of this, so 1 minus 1 over b. And of course, this is a number over something approaching infinity. So this is going to be 1 minus 0 or 1. So we would say that this integral as b approaches infinity converges to 1. We can interpret this improper integral as the area of the unbounded region between the graph of f of x equals 1 over x squared and the x-axis. So if we think about this whole thing here, the area under that would be 1. So improper integrals with definite integration limits. If from a to infinity of f of x dx, then that's the same thing as the limit from b to infinity of the integral from a to b of f of x dx. We just did one like that. You could also have negative infinity on the left, or you could have negative infinity and positive infinity. You're looking at the area under the curve over the entire function. And in that case, what you typically want to do is pick a point C in the middle and just split it up and do each of types 1 and 2. So we'll look at a couple of different examples. Here I've got the integral from 1 to infinity of 2 over x dx, and 2 over 1, there's no problem with that. So what I'm going to do is I'm going to make this the limit as b approaches infinity of the integral from 1 to b of 2 over x dx. And I'll start by bringing out this 2. I'm going to skip over the integral and bring it all the way out to the limit because there's no problem with that. And I'll have the integral from 1 to b of 1 over x dx, which we know is the natural log of the absolute value of x, from x equals 1 to x equals b. So that'll give me 2 times the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of 1. And of course, this is 0. So I have 2 times the limit as b approaches infinity of the natural log of b. And let me just write this a little clearer. This is the limit. This is the natural log of the absolute value of b. And as b approaches infinity, the natural log of b approaches infinity, so this is twice infinity or infinity. Anytime you get the answer infinity or negative infinity, we say that this integral diverges. You can't calculate the area under the curve of this function because it just keeps growing forever. Here's another example. We've got the integral from 0 to infinity of e to the negative x dx. So with this one, I'm going to again write the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. So in this case, my u is going to be negative x, which means I need a negative here in order to have du. And I'll just bring that other negative all the way out to the front. That's going to cancel it. So I will have, actually, let's put it here. I say all the way out to the front. Let's just stick it right here. Okay, so we'll have the limit as b approaches infinity of negative e to the negative x from x equals 0 to x equals b, which will be the limit as b approaches infinity of negative e to the negative b minus a negative e to the 0. And that is the limit as b approaches infinity of 1 minus 1 over e to the b power. And I do it this way for a reason, because this fraction is a number over something approaching infinity, so the whole fraction is going to go to 0, which means that this limit is 1. So we can say that this one converges to 1. This is an interesting example because we go from negative infinity to infinity. So I just need to pick a c in the middle to break this up. I want it to be something where the function is defined at that point. And I'm going to pick c equals 0 because 4 divided by 16 plus 0 squared, there's nothing wrong with that. We can use the c equals 0. So we'll make this the integral from negative infinity to 0 of 4 over 16 plus x squared dx. And the integral from 0 to positive infinity of 4 over 16 plus x squared dx. So this one's going to be a limit on this side, so we'll have, I'm going to bring the 4 out front, and we'll have the limit as a approaches negative infinity of the integral from a to 0 of 1 over 16 plus x squared dx. This one's on the lower bound, plus 4 times the limit as b approaches infinity of the integral from 0 to b of 1 over 16 plus x squared dx. So you can see that I brought the 4's out, and then I replaced that negative infinity with the limit as a approaches negative infinity, and I replaced that positive infinity with the limit as b approaches infinity. Now for both of these integrals, I recognize an arctangent form where u equals x and a equals 4, so it's a squared plus u squared. And that's not the same a that we have here, just make sure you're clear on that. So when I evaluate that, I'm still taking the limit. Here I'm going to get 1 over a, so 1/4, arctangent of u over a, x over 4. And that's all going to go from a to 0. And here, I'll have the same exact thing, but the bounds will be different. Okay, so a couple of things that can happen. We can cancel the 1/4 and the 4's on the outside. So I will have the limit as a approaches negative infinity of the arctangent of 0 over 4, which is 0, minus the arctangent of a over 4, and we are talking about this a, plus the limit as b approaches infinity of the arctangent of b over 4 minus the arctangent of 0. Okay. And we know that tangent of x, if this is pi over 2 and this is negative pi over 2, if you think back to its graph, you know that it makes this nice pretty curve, and we know that the arctangent of 0 is actually 0. So I'm really just looking at the limit as a approaches negative infinity of the negative arctangent of a over 4 plus the limit as b approaches infinity of the arctangent of b over 4. Now again, as a approaches negative infinity, the arctangent of a is going of that a over 4 is basically what angle do we approach as the y value of tangent approaches negative infinity. So you can see from this graph that as the y value here approaches negative infinity, the angle on that side is approaching the negative pi over 2. And on the other side, as the y value is approaching positive infinity, you can see that the angle is approaching positive pi over 2. So we're going to have the negative pi over 2 plus the positive pi over 2, which is pi over 2 plus pi over 2, or pi. So this one converges to pi.